Bismillah ar-Rahman ar-Rahim. In this lecture, we're going to speak about finding the volumes for irregular shape. As we did for the volume, we have some shapes that are regular, in which that we can find the area directly by the formula when it is like, for example, triangle, it is half the base multiplied by the height, or rectangle, which is the area is equal to width multiplied by length, or a circle. But if we have a irregular shape, for the area, we slice the curve or the partition, the interval from A to B, and then we draw small rectangles, and then we found the sum of all these area of the small rectangles. For the volume, we have the same concept. If we speak about the regular solids, for example, if I have cylinder, we know that the volume is equal to A multiplied by H, where A is the area of the base 1 or base 2. So it is A multiplied by H. It is the area of the base multiplied by the height of the cylinder. If we have circular cylinder, for example, then V is equal to P by R squared, because the base is a circle. So A is equal to by R squared, multiplied by the height. That will give me the volume of the circular cylinder. If it is a rectangular box, then we multiply the three dimensions. It is the height, length, and the width. That will give me the volume of the rectangular box. But in some cases, the shape is irregular, like this. And we need to calculate the volume for this shape. As we did for the irregular shape, or finding the area of the irregular shape, we are doing the same thing for the volume. We slice or find the cross section for this shape, just make it in small slices. Then we find the delta x, which is the width of that slice multiplied by the cross-sectional area. So let's speak about the cross-sectional area now, multiplied by the width of that slice. Then we add all of these together to find the volume of the shape. Or, to make it formal, we say that let S be a solid that lies between x equal to A and x equal to B. A and B. If the cross-sectional area of S in the plane Bx is through x and perpendicular to the x-axis is A of x. So this is the area of the sectional area. We call it AX. So I have something. This is AX, and it has some width, delta x. The volume for this one will be given by A x delta x. Now, if you add all of them, find the sum for all of them as n goes to infinity, then we can define the volume of the solid. So the volume is equal to limit of sigma from as I from goes to from 1 to n of AXI, the area of the cross-sectional, multiplied by delta x. As n goes to infinity, this can be written as integration from A to B of the sectional area, AX multiplied by dx. So the volume is just the integration of the sectional area A of x from A to B. Let's have some examples to explain this concept. Sometimes we can find the volume of solids by revolution, which means to create the volume, what I need is just to rotate the shape about x-axis or y-axis. For example, if I have this function, this is f of x, and if we take typical rectangle there, now if we rotate it about the x-axis, just rotate it about x-axis, we will have cylinder. This is the function. Then we have a cylindrical shape. If we just rotate this part, it will be cylindrical shape. And the volume for the cylindrical will be the height, delta x multiplied by the area. Now, if we integrate this from A to B, we'll have the volume of the solid by that will is already revolved or rotated about the x-axis. We'll have shape like this. And then we need to find the volume for this shape. For example, find the volume of the solid obtained by rotating about the x-axis, the region under the curve y equals square root of x from 0 to 1. So my curve is y equal square root of x. And we need to rotate this curve about the x-axis. If we do this one, we know that the function y equals square root of x is take this shape. So this is y equals square root of x. Now the typical rectangle, which is this one, if we rotate it about x-axis, we will have disk. We call this a disk. Now the disk is just a cylinder, circle, and there is height. This is cylinder. And the volume of the cylinder is given by A, x, means the area of the base multiplied by the height is delta x in this case. So we are using delta x as the height or the width of the cylinder. Now for the area of the base, we think about it. This will be my radius. I have circle. The r itself is given by square root of x, which is this function. So ax is equal to by r square. But r is given by square root of x. So it is by square root of x square. That will give me by x. And this disk is just, it is like moving disk from A to B, from 0 to 1. So to find the volume in this case, volume will be integration from 0 to 1 of A x dx, which is equal to from 0 to 1, ax given by x dx, which is equal to y multiplied by 1/2 x squared from 0 to 1. Now just apply the fundamental theorem of calculus to evaluate this one. We will have y equal to 1/2 multiplied by 1 minus 1/2 multiplied by 0. I will have pi over 2. So pi over 2 will be the volume of this shape given there. So this is the idea of finding the volume by revolution. If we have a curve, we revolve that or rotate that curve about x-axis or y-axis. Sometimes it's about the x-axis. Some other cases we are going to use the rotation about the y-axis. We see the shape already created, then we find the volume by integrating ax dx to find the volume. Another example. Suppose that we need to find, or that region is R is enclosed by the curve y equal to x and y equal to x squared. Now I have this function y equal to x, which is a line across the origin, and I have y equal x squared, which is a parabola. Is rotated about the x-axis. And we need to find the volume of the resulting solid. So if we graph this function, or the two equations, y equal to x and y equal to x squared. Y equal to x is just a straight line. It is this one. This is y equal to x. and this is y equal x squared. So my R is this one, the enclosed between the two equations. Now if we rotate this about the x-axis, we have to be careful about this part. This part, we say it in black now, is not part of the solid. So like we have a hole or some empty area in the rotation. So if we rotate it, we'll get this shape, but this will give me something called the washer. Washer means that we have a big circle and another small circle and empty space in the disk. It is not a full disk. We have some empty space or area. So if we rotate what's given there, that shape, we'll have washer. We call it washer. Now the area for the cross-sectional is just the shaded one. And this one, it is like A1, the big one minus small circle. It is the area of the big circle, which is R, big R, and the area minus the area of the small circle. We think about it. Now this is my typical rectangle. Big R is the upper one. It is y equal to x. So I can say A1 is given by, if we think about A1, the big one, it is by R1 squared. That will be by x squared. Okay, big R is the upper one. That will give me by y equal to x. A2, take the lower function. That will be by R squared. That will equal to by of. The second one is x to power 2, which is x to power 2 or to power 2, which is equal to by x to power 4. Now, if I want to find the shaded area for this cross-sectional, it is A1 minus A2. A1 minus A2, which is equal to by x squared minus by x to power 4. We can take by as a common factor, so it will be x to power 2 minus x to power 4. Or we can say in general for the washer, the shaded area will be by R1 square minus R2 square. The outer radius minus the inner radius, R1 square minus R2 square. Now I have the area of the sectional or cross-sectional area. We have it. All what I need to integrate the cross-sectional area. So the volume in this case, integration of. Now A and B is given there in the figure. It is from 0 to 1. It's just the intersection point. If it is not given, then we can find A and B. To find A and B, the limits. This is to find the interval. Okay, it is a line and parabola. Come on, let y1 equal to y2. That will give me x equal to x squared. Or I can write it as x squared minus x equal to 0. We can take x as a common factor. It will be x minus 1 equal to 0. So either x equal to 0 or x equal to 1. Again, the intersection point means y1 equal to y2. So we have equation, quadratic equation, and we solve it to find the solution for this equation. This will be A and B. So the volume in this case will be from 0 to 1. of cross section AX dx, which is equal to from 0 to 1 of pi multiplied by x square minus x to power 4 dx. Integrate and evaluate. Now we will have pi multiplied by 1/3 x to power 3 minus 1 over 5 x to power 5 from 0 to 1. Replace x by 1 and then replace it by 0. We will have pi multiplied by, this is 1/3 minus 1 over 5 minus 0. That will be pi 1/3 minus 1 over 5. That will be equal to 2 over 5. It is 5 and 2 over 15. That equal to 5 minus 3 divided by 15, which is equal to 2 pi over 15. So the area for this shape, again, I'm finding the area of this shape. By rotating about the x-axis, we have the volume is equal to 2 pi over 15. And we can write the unit as a cubed unit. Must be centimeter or meter or inch or whatever, just a cubed unit. So this is the idea of finding the volume created by rotating about x-axis, or in the coming lecture, I'm going to speak about the y-axis also. I can rotate about x-axis or y-axis. And the rotation, or the rotated solid can be created by solid disk or by washer. If it is solid disk, then it is ax times dx. If it is washer, then we have to find the shaded area by subtracting the radius of the bigger one minus the smaller one.